I haven't met Professor Diktiarev before, but I want to yeah, I'm sorry, I'm not really from the community of real geometry. But I want to say that my journey of real algebraic geometry was initiated by reading the book that you wrote, joint with Slava and Ilya. That was the beginning of my interest in this topic, and I hope it will continue, inspired by all the good mathematicians in this community. Okay, so I'm going to talk about today some work that I've worked out with my old postdoc, Andrea Cattaneo, about 3-4 years ago on hyper-Kähler manifolds. So it's a mixture of complex geometry and real geometry. So I will start with the basic notion. I don't know if it is necessary, but let me nevertheless cover the basic. Okay. Let X for X a complex manifold. A real structure is, by definition, an anti-holomorphic involution. Yeah, I see it's not necessary to say it here. And for a complex variety, algebraic variety, defined over C, a real form is a real variety, is an algebraic variety x0 defined over R. That's a scheme over finite type over R, such that when you base change to spec C, you get back X as a C scheme, as a C variety. As C varieties, okay? There is a natural equivalence relation among real structures by conjugation. And the obvious equivalence relation among the real forms are isomorphic as R varieties. And in fact, when the two notions apply, they coincide in the following sense. So if X is a, say, smooth algebraic variety defined over C, then on the one hand, we can look at the real forms on X. And on the other hand, we can look at the real structures on the complex manifold of complex points. And they are bijection in the precise sense that if we quotient out by isomorphism as R schemes, and here are quotient out by the conjugation relation, then we get a bijection. Okay. To go from here to here, you just take any real form. You look at its conjugation on the second factor, and you transport it to the right-hand side. You get a real structure. And in the other direction, you just do the quotient. You take the sheaf of algebras, you take the invariant, you take the spectrum, you'll get back the real scheme. Okay, so that's the basic object that I'm going to study. And the goal, like the ultimate goal for this kind of question is that if X is a complex algebraic variety or a complex manifold, we can ask whether there exists a real structure, existence of real structures. Okay, that's a question. So obvious necessary condition is that X is isomorphic or biholomorphic to its conjugate complex manifold. And if there exists some real structure, are there only finitely many? So finiteness of real structures, finiteness of real structures. Okay, it's another question. And ultimately, we would like to classify all the real structures. Okay. All these are interesting questions, but of course we can ask many more, like deformation or things like that. But in today's talk, I will concentrate on this second question, finiteness of real structures. on hyper-Kähler varieties, as you can already guess. Okay, before talking about finiteness results, let me first transform this question of finiteness of one of these sets into something more cohomological. It's called a non-commutative group cohomology. I guess it's also not necessary, but let me just say it. Non-commutative group cohomology. Cohomology. Okay, what is this? So if you fix a finite group, let me call it gamma. It will be z over 2 for real geometers. It acts on some other group, so it's just a group with gamma action by automorphisms, the action by automorphisms. We can define the so-called first group cohomology set of gamma with value in A. So this, by definition, is some quotient set of. So it's a set of one cocycle, quotient by not co-boundary but some co-boundary relation. So it's some map, not a group homomorphism, but just a set of maps satisfying some cocycle conditions. It's like phi gh is equal to phi g phi h. But then you want to twist it by g, because g acts on A, so you can twist it. So this set is called one cocycles. It's not a group, but it's a set. And then you quotient out by some equivalence relation where you declare that phi 1 is equivalent to phi 2 if we will have two cocycles. They are equivalent if and only if there exists some element A in A such that phi 1 and phi 2, they are conjugate by this A, more or less. A like A inverse A, then you want to twist it by G, okay? For any G. Okay. So this is just, this is the pointed set. This is pointed set. So it's a set, not a group, but there is distinguished element that is to map everything to the neutral element. And as usual, if you have a short exact sequence of groups that are preserved by gamma, you get not so long exact sequence. So you go from the invariants, then H1, 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 you stop there. And if A is commutative, then you go, recover the classical notion of group cohomology. Then of course you can go to a higher cohomology. No, yeah, that's non-commutative means that A is not abelian. Oops. Group not necessarily abelian. Yes, that's why I write down the definition. Otherwise, I think it's not necessary. Any other questions? Okay, then the upshot is that there is. I could write the name Borel cell, but they don't. The following does not really need a Borel cell to prove it. So there is a bijection between this set. Oh yeah, let me gamma to be the Galois group of C over R. So not so complicated. So X is a say complex manifold or complex variety, algebraic variety. They both work. So. And I take automorphism group of A. It's just the holomorphic or algebraic automorphisms, depending on the context. Automorphism of X. And there is a bijection between, yes, I forgot to say, and the gamma X, of course, on the automorphism group. Yeah, okay. Let me erase something to gain some more space. If, suppose, there is a real structure, let's call it sigma 0 on X, okay? Otherwise, it's an empty set, nothing to talk about. If there is at least a real structure, then I can define an action of gamma on this group by sending, how to say, by conjugate, by conjugate by sigma 0, okay? That's an action of Z2 over that. Then there is a bijection. Then the conclusion is that we have a bijection between the non-commutative group cohomology of gamma, which acts on this group, so this makes sense, is a pointed set, together with any of this set, okay, we are interested in. So let me just take real structures. on X quotient by conjugation. Okay. Why this is true? Well, it's very easy to see. Well, if you have a real structure, no, let me take a one cocycle here. So one cocycle is a map from gamma to the automorphism axis. But gamma is just z over 2, so I can look at the non-trivial element. Maybe let me call it conjugation, the only non-trivial element there. And I still call the image phi. Sorry for that, because it determines phi. Then the real structure on it will just be, I guess, phi sigma 0. The one cocycle condition tells you that this is an involution, and this is obviously anti-holomorphic because phi is holomorphic. Sigma 0 is anti-holomorphic, so their composition is anti-holomorphic. So the result is that this is a bijection. So now the finiteness problem of these two sets is transferred into a finiteness question on this non-commutative cohomology set. Okay? So let me try to write down some finiteness results here. Yeah, please, if there is any question. Okay. Yeah, the first result is really easy. Okay, it's not my result. Okay, obviously, it's like if. Oh, how to say? Let me write it in a more obvious way. Okay, if A is a finite group, then H1 of gamma A is finite. Okay. This is obvious because of the definition. Okay, this set is obvious. Well, using this result, you can already see. So yeah, let me do parallel finite list of real structures. So if let me say X is a general type, then we know that automorphism group is finite. This is a classical result of Matsumura, I think. Anyway, this is. Sorry? Matsumura, 1963. Oh, okay. Thank you. 1963. Thanks for the reference. Yeah, I really don't know the reference. I just know the name. Okay, so if it's a general type, then it's a finite group. Then you apply this result, you see that there are only finitely many real forms. And second result is less obvious. I guess it's due to Serre. If A is an algebra group, A is, let's say, let me put AR, connected algebra group, real algebra group. Let me denote by A the complexification. So it's a complex algebra group. Then we know that H1 of gamma in value with values in A is also finite. This result you can find in Serre's book, Cohomologie Gaussienne. Right. Well, his book only covers like A is a linear algebra, connected linear algebra group, but if there is any abelian factor by Chevalier structure, you can also figure out by lowering the sequence of the group cohomology. That's not so difficult. Okay. One corollary is that actually if yeah, let me write it in this way. If AR is a locally algebraic group over R, A is still the complexification. Okay. Then yeah, let me call A0 the identity component of A. Then yeah, H1 of HA1 of gamma with value in the pi0 of the group, which is a discrete group this time, is finite. Then it implies H1 of gamma of A is finite. So in some sense, this corollary tells you that you can neglect the continuous part of the locally algebraic group. You are only concerned with the pi0 of the group, the discrete part. Okay, and a corollary of this, of course, is just that I can remove the word connected. Okay, because for algebraic group there are only finitely many components. Okay? So okay, with this criterion, we can also get some nice examples with finite many real forms. For example, well, if you take a Fano variety, Fano manifold, then you know that the automorphism group of X is an algebraic group because you can write it in differently as K, like, I don't know, okay, minus Kx. Okay? It's just, this then is finite. Oh, sorry, it's algebraic. Okay? So these two cases, they all have finite real forms, finitely many. Okay, I don't think I can write parallel here. Maybe I have enough space. 3, I'll try. Another some kind of major result is Borel-Serre in their French paper on this non-commutative cohomology. It says that if A is arithmetic group, so here it means it's a bit more subtle. It means that you have a linear algebra group which also has a gamma action, and you can, if you can embed A into that linear algebra group, and such that A is commensurable to the integral points of that linear algebra group, then this is called a arithmetic. I probably should put a gamma arithmetic group. Yeah, but if A is a arithmetic group, then this is also finite. This is a Borel-Serre's paper. Gamma arithmetic, but yeah, I don't want to write gamma actually. If A is an arithmetic group, then the group cohomology is finite. Yeah, a very nice consequence is that if X is an abelian variety, abelian variety or even a complex torus, then there are only finitely many real structures because this implies that the automorphism group of A, and I said that we can mod out the connected component for free, but this is arithmetic. All those are explained in the paper of Borel and Serre. Okay. Yeah, it's basically isometry, like symplectic isometry of the lattice. And by definition, it's an arithmetic group. It's yeah, the lattice. No?
I mean, if you don't take a polarization.
Maybe you're right. Maybe I should, let's see.
I mean, if you say.
You're right.
If you take a polarized abelian variety, then it's something, and otherwise I don't understand.
You're right. Maybe I should strike out complex torus. I'll do that. It just takes some time. Yeah, you're right. Okay. Sorry? No, no, this group is arithmetic. Just. Why do we need polarization? I mean, abelian variety is the. Yeah, V over gamma. I think it works for a complex torus too. It's just V over gamma, then you somehow maps gamma to gamma, and it's a arithmetic group. Okay. Good. The parallel continues. Okay, so in particular, in dimension 1, any smooth projective curve admits only finitely many real structures, okay, Fano, general type, and abelian variety, elliptic curves. Well, now you can ask what happens in higher dimensions. Yeah, before that, let me tell you another story which covers in particular surfaces in Kodaira dimension equals to 1. I mean, fibered surface is that if, what's the best way to say it? Okay. Some not so difficult lemma, which is indeed, I learned from the book that you three wrote, real enriched surface, and there is some lemma sketched, and we wrote it, the proof again in our paper. It says that if, let me call it dévissage, okay? Dévissage. It's if there exists a finite filtration by normal subgroups, let's say A, let's call it A0, then you have A1, A2, and it stops at some finite length, such that all the graded associated, so for any I, H1 of gamma of AI quotient by AI plus 1 is finite. For example, if AI quotient AI plus 1 is finite group, or like finite generated abelian, this is really interesting case. Then we can conclude that H1 of gamma A is finite. Okay, it's like a usual long exact sequence. You get long exact sequence trick, but of course you have to use some trick of twisting. I won't say any details here. But this is a dévissage lemma. For example, this if a group that is solvable and all the graded associated pieces are finite abelian groups, then you can apply this lemma. Okay, so this in particular implies that a very interesting case is that if for any, let's say, for any phi automorphism of X, we have phis of zero entropy. Okay, it means that dynamic degree, first dynamic degree is 1. Then there are only finitely many real structures. Real structures on X is finite. The reason is that for those kind of dynamically uninteresting varieties, there is a paper by Dean Ogiso, De Gizang, who else? Dean Ogiso, Xiu Yong Lin. Then the automorphism group is solvable. As I said, they have like graded pieces given by finite abelian groups. Then you just apply this dévissage, you get the finiteness. Okay? Why this is interesting? So for example, how do we apply this kind of condition? For example, if the Kodaira dimension of X is equal to the dimension minus 1. So when I said general type, it says the Kodaira dimension equals to dimension. But if it's only 1 lower, then it satisfies this condition. This is also a work of this is also work of Dean Ogiso and their collaborators. Then star holds. Okay. So in particular, now you see for many surfaces, we can have the positive answer. For example, if it's Kodaira dimension 1, covered by this lemma. Kodaira dimension 2 is general type. Kodaira dimension 0, it's the main subject, which has taken up by Sasha and Slava and Ilya in your books, in your book and papers. And also for like rational surfaces, it's really interesting. I'll come to that in a minute. And for irrational but root surface, then you can use like Albanese fibration, which is also canonical under automorphisms. Then you use the same trick. You see that there are only finitely many real structures. So the upshot is that in dimension 2, there is a very recent paper a few weeks ago by a bunch of authors. I have to write them. Dean Ogiso, it's always the same, but there are some other names. Gachet, Xiu Yonglin, Ogiso, and Wang Long, Yu Xun. Yes, okay, this is really recent, a few weeks ago. So they said that if X, a smooth projective surface, complex surface X has infinitely many real structures up to conjugation, then it has to be of the following type. Then X is birational to P2 or K3 surface or enriched surface. Okay, surface. So it's really quite, in my opinion, it's quite precise, a control. So any surface of different birational type, they only have finitely many real structures. Actually, in their paper, they went through some argument to rule out surfaces that is birational to bielliptic surface, and also ruled out birational to abelian surface. There are some argument needed. But this is really complete. I have to say that the initial project to classify these kind of things is also in your work. Even before, even before in the Russian school. Many work has been done in that direction. And this is the most updated state of art. Okay. And also, there is a second part in their theorem that I find it very beautiful, that I want to present here, is that all these cases occur. All these cases occur. Namely, they can, let me only say it, not write it. For, I think, first of all, Dean and Ogiso, about 3 years ago, they constructed, all these cases occur as surfaces with infinitely many real structures, okay? So Dean and Ogiso 3 years ago, they constructed a K3 surface blown up at many points with infinitely many real structures. Then a few years later, Dean and I think Dean, Ogiso, and Yu, they construct the K3 surface blown up at one point. And actually, in the same paper, or maybe a different one, they construct a rational surface with infinitely many real structures. And in this paper that I talked about a few weeks ago, they constructed an enriched surface blown up at the one point that has infinitely many real structures. Okay. Yes. Now, here comes to the main point. Obviously, I haven't seen the most important result for my talk in dimension 2. That is, there are only finitely many real structures for K3 and enriched surfaces. Not blown up, just the minimal one. I think I can use that. So the 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. So K3 surface and enriched surface has only finitely many real structures. Okay, so this is in the book of Sasha, Ilya, and Slava. Right, and this is the result that I want to generalize in this talk. So the question is to generalize it. So today we are going to generalize this 5 to higher dimensions. Okay. So what is the higher dimensional analog of K3 surface and enriched surface? Well, for K3 surface, it's called hyper-Kähler manifolds. And the enriched surface, there is some manifold called enriched manifold, which is also quite similar to that. Let me recall the definition, okay? I don't think it's a kind of common knowledge in this community.
I got distracted a little bit, but you first say that there are infinitely many real structures, and then you wrote that there are
yes. So, yes, that's why I didn't. It's a birational. Birational. Yeah, but not in all cases with not. Yeah, all cases. Yeah, it's like all birational cases. Yeah, all birational cases. I'm sorry. Yeah, actually, any minimal surface also has finitely many real structures. So I said that they have to blow up one or more points in that case. Okay, let me tell you what is the hyper-Kähler manifold. So a compact Kähler manifold, so complex manifold X is called hyper-Kähler. Can you see this here? Hyper-Kähler. That I just write HK for simplicity. If just to decompose into a simple factor, let's assume that the fundamental group is trivial, and the most important condition is that the existence of a holomorphic two forms. So I assume that the holomorphic two form generates the space of two forms. Sorry, the space of a holomorphic two form is one-dimensional, such that the generator is non-degenerate, meaning that hyper-Kähler manifold is always even-dimensional, complex even-dimensional. This wedge n times top form is nowhere vanishing. It says that it is a symplectic form, algebraic symplectic form on each tangent space of any point. So this in particular, this is Calabi-Yau. X is Calabi-Yau, okay? So actually, this hyper-Kähler variety is one of the building blocks of Calabi-Yau manifolds by a theorem of Bogomolov. They show that if you have a compact Kähler manifold with first Chern class trivial, then you can take a finite 8-dot cover, a covering space, finite covering space, such that the covering space is a product of abelian, complex torus, times some strict Calabi-Yaus, and times some hyper-Kähler manifolds like this. So they are really building blocks of that. Let me also give you some examples, just to give you some ideas. In general, those kind of varieties, they are quite difficult to construct, unfortunately. But still, we have some nice examples. In dimension 2, they are just K3 surfaces. Okay? Then, if you start with a K3 surface, then you can take the Hilbert scheme of points on that K3. Where S is K3. Sorry?
It's not an example.
Why is not an example?
It's okay. We all know what is a K3 surface and the example, but you wanted to give an example.
Okay. You want some? Okay.
The quartic surface in P3 is an example.
Okay, that's right. Right. Quartic surface in P3, intersection of quadric and cubic in P4, intersection of 3 quadrics in P5, intersection of. Do you want me to continue? Intersection of quadric and two hyperplanes in Grassmannia 2.5, things like that. Okay. Here the scheme is K3, yes. So this is by Fogatti, this is a smooth projective variety, and this is a hyper-Kähler. And more generally, you can look at the moduli space of sheaves, some stable sheaves, moduli of stable sheaves, with some nice choice of the topological data and the stability condition. You get hyper-Kähler. This is a result of Mukai, Yoshioka, many people, Goethe, etc. And also, starting from abelian surface, you can do a similar thing. So you can look at the so-called Kummer. So A is an abelian surface. This is just a fiber of the following map. So Hilbert scheme, you start with an abelian surface. Unfortunately, this is not simply connected. It's almost like this, but it's not simply. Yes, that's why I said for, yeah, okay, you want me to come. Moduli of stable sheaves with V primitive and HV generic. That's the precise statement. V is the Mukai vector. Sorry? What's the question? Maybe I didn't understand.
I thought these are singular.
No, this is S a K3 surface. Maybe S is K3. This is a theorem of.
I think that's what O'Grady and other people did. They take a symplectic resolution.
Yes. But if you take V primitive, V is a primitive Mukai vector, then it's smooth projective. In O'Grady's example, V is twice of a primitive vector, and that emits some symplectic resolution. Yeah. Yeah, it's a primitive, really important, and the stability condition has to be generic, so that semi-stable coincide with stable. Okay, then we continue. For an abelian surface, you can do the same trick. You have here a scheme. This is smooth projective variety, but unfortunately, this is not simply connected. But it's just a bunch of points. You can add them. So you get a map to A, and you take a fiber of it. This will be simply connected and satisfy all these conditions. This is called the generalized Kummer varieties of A. In fact, if you take n equals to 1, it's just the Kummer surface of the A. And similarly, you can take the moduli space of stable sheaves with primitive Mukai vectors and V generic stability condition. And it will not be simply connected, but if you take the Albanese fiber, then it will be another type of hyper-Kähler varieties. If you want more geometric examples, maybe I can give you one of them. So if X is a cubic fourfold, so a smooth hypersurface of degree 3 in P5, then the lines of X, lines contained in X, this is a 4-dimensional hyper-Kähler manifold. Okay, so this is naturally a submanifold of the Grassmannian. And this is a 4-dimensional hyper-Kähler. One very important thing is that any deformation of hyper-Kähler is again a hyper-Kähler. So it's a long story. It's a whole subject of study. It's a very nice variety. Their deformation theories are unobstructed. They have a nice period map. You can understand them more or less, at least up to birational, by using their Hodge structures on H2. And even if it's not a surface, you can still endow the second cohomology with a quadratic form called the Boville-Bogomolov quadratic form, which makes it really like a surface. So the principle is that whenever you know a theory or some results on K3 surface, you should try to generalize to hyper-Kähler manifolds. So this is exactly what I want to do today. Okay. Yes, I also want to say that it's very easy to produce some natural real structures if you have a real structure on the surface. Okay? If you have a real structure here, you can induce some involution, which will again be anti-holomorphic. Similarly for the other choices. So such kind of manifolds, they're higher dimensional, they admit some interesting real structures, and the question is whether they are only finitely many. So the theorem is that it's indeed the case. So let the main result. Yes. So let X be a compact hyper-Kähler manifold. Then the first theorem enjoined with Catania is that there are only, let me just write, real forms, real structures on X. Up to conjugation, there are only finitely many. Okay, so that responds positively to the question that I asked. So it's a generalization of your result. Okay, theorem 2. Yeah, it's always due to joint with Daniel. Okay. Theorem 2 is that it actually not just about real structures. It's about some finiteness result of the automorphism group. Okay, so for automorphism of X, and even the birational automorphism of X, there are only finitely many finite subgroups up to conjugation. There are only finitely many finite subgroups. Not quite, up to conjugation. Okay. Theorem 3 is that these groups, they are finitely generated or even finitely presented. Okay, so we were originally interested in like real structures and finiteness, but somehow we quickly realized that it's really a property about the group. Okay, let me give you some remarks before giving ideas of the proof. The first remark is that for non-projective ones, they are not difficult. If X non-projective, so outside of algebraic world, then we have the theorem Ogizzo showed that these groups, they are almost finite generated abelian. How to say? Almost abelian of finite rank. Showed that automorphism of X and the birational group of X are almost abelian of finite rank. I think that's the terminology. Almost abelian of finite rank. I will explain. That means there is finite index subgroup G such that G quotient by G0 is like Z to the R with G0 a finite group. Okay, so up to finite kernel and co-kernel, this is just the free abelian group of finite rank. Okay, this is really strong theorem on the structure of these groups, and using the structure and the dévissage, maybe it's still there. Yeah, still there. The dévissage with a little bit more trick. You can show that the H1 of these things trivial and blah blah. You can show all the results. Not so difficult. So we will concentrate on the algebraic setting. Assume X projective in the sequel. Okay. Second remark is that theorem 1 is not really the main result. Theorem 2 actually implies it. Theorem 2 implies theorem 1. Why is that? I need to introduce another slightly bigger group. It's called the Klein automorphism group. That I just denote by K out, following the notation in your book. I think so. Yeah, it's yeah. They are just automorphisms of it's diffeomorphism of X, such that G is holomorphic or anti-holomorphic. Okay. So it's automorphism group is a finite. Is a subgroup of it of index at the most 2.
Actually, they were called di-analytic.
Sorry.
They are called di-analytic.
D-analytic. What? D-I-A?
D-I-A-N.
Oh, analytic. Okay. Okay, thanks.
This was given 50 years ago or something.
Ah, okay. Okay. Yeah. Good. So the argument is really easy. So we want to show that H1 of gamma with value in automorphism with the action I explained, conjugation by sigma 0 if there exists at least one real structure. We want to show that this is trivial. Sorry, we'll show that this is finite, but this actually it can be, how to say, this is implied by the same group with slightly bigger value, K out is finite because more by dévissage. They are just index 2 subgroup, okay? But this, because the conjugation by the real structure is the inner automorphism of this group. So we can change the action. So this is equivalent to the finiteness of the same cohomology, but with the action of gamma on it is trivial. Okay? So we want to show that this is trivial. But however, yes, we want to show that this is trivial, but so the action of gamma on this group is the conjugation by the fixed real structure. But here the action is trivial. But they are in bijection. Yeah, they are in bijection. But this set is just the by definition, it's just the conjugacy classes of order 2 subgroups up to conjugation in this group. And by the theorem, I didn't write K out, but yeah, we can show the same thing for K out. And that is implied by theorem 1, theorem 2, yeah. Okay? So in the end, it reduced to some finiteness of finite groups in this bigger group. Okay? By twisting the action. Okay, so in the last 15 minutes or so, I will try.
Why the if it has a finite number, why is this cohomology? Theorem 2 implies that this group is finite.
Yes, this is by definition. If you look at the definition, I think it's already erased. Is that, so what is this group? This is like a cocycles modulo sum relation. But a cocycle for trivial action is just a homomorphism of groups. So gamma is Z2, yeah? So they are classifying order 2 subgroups up to some relation. That relation is exactly conjugation. Yeah, I didn't explain. It's H1 for trivial action, just a homomorphism up to conjugation. So it's just, literally the same theorem 2. Okay. Oh, I also have to say that after our paper is published, these theorems they acquired new proofs, somewhat new proofs. One by Kernozov, Yasinski, the other more recently by Teppei Takamatsu, and some somewhat different proof, but all of the proofs use the same ingredient, use the same most important ingredient. And I guess our contribution was like to realize that this kind of theorem is more or less equivalent, it's implied by the so-called Morrison-Kawamata Kohn conjecture that I'm going to explain now. So all the proofs uses the following main ingredient. So it's a conjecture usually attributed to Morrison and Kawamata. Two? Theorem 2, now, even theorem 3 is also quite a direct consequence of this conjecture. Morrison-Kawamata conjecture, Kohn conjecture. Okay, it says the following. So if X is smooth projective with a trivial canonical bundle or even numerically trivial canonical bundle, let's not distinguish the details here. Calabi-Yau manifolds, then the action of the automorphism group on the ample cone, or rather, I should say the Neff cone. So Neff divisor is all the divisors that intersect all the curves non-negatively. They form a cone in the narrow Savory space. If you multiply by the real, positive reals, it's a cone, and the automorphism group acts on this cone by pulling back. Then this action has, more precise, I should put a plus here, but let's not go into details here, has a rational polyhedral fundamental domain. Polyhedral fundamental domain. Rational polyhedral fundamental domain. So fundamental domain is just a closed subcone such that all the translates by this group, they covers the whole thing, and all the interiors of their translates don't intersect. That's a rational. That's the definition of fundamental domain. And the rational polyhedral means that that subcone is cut out by closed half space defined by rational vectors. Yeah. No, it's a finite on the nose. Rational. Yeah, I should usually people put a finite, but I think the literature of today they don't they drop the adjective. It's really called a finite rational polyhedral fundamental domain. Yeah. That's the Morrison-Kawamata Kohn conjecture, and there are some known cases. Known for so for case 3, for enriched surface. So for case 3 surfaces, this is a result due to Stirk. Enriched surface, this is due to Namigawa. And these, I think, are ingredients that you used in your book to prove the finiteness of real structures for K3 and, where is it? For K3 and enriched, okay? And indeed, we are also going to use the same, okay? So for some Calabi-Yau's, here the results are really sparse, I would say. I invite you to read like surveys of Piternel, Lazich, etc., Ogiso, etc.
I mean, is the outband generated by the reflection of the faces?
No, that's not true. That's not.
It's true or something,
Yes, so if, yeah, I will come to that. But if it's a K3 surface, yes, what you said, you have like -2 classes to cut out the ample cone, and you have a reflection with respect to the -2 curves, -2 classes. That will give you a fundamental domain of the whole positive cone. That proves that the ample cone is the fundamental domain of the whole positive cone. Then automorphism group cuts further the ample cone into fundamental domains that is smaller but finite. So the ample cone itself is not finite. It could have quite a complicated boundary. But the fundamental domain is really finite. That's the origin of the finiteness result here. And the most important result is that for hyper-Kähler is known. This is a major result of Amerik, Verbitsky. So yeah, that's actually our motivation to work on this project. When we saw they worked out the Morrison-Kawamata cone conjecture for hyper-Kähler, we realized that we should be able to deduce everything for hyper-Kähler. That's our work. Okay, so we will use this ingredient. I don't know if I have 5 minutes. Okay. So as I said, all the proofs that came after, they all in some sorts use this hyper-Kähler Morrison-Kawamata cone conjecture as an ingredient. And actually, the most recent preprint that I mentioned of many authors somewhere, they write down clearly that Morrison-Kawamata cone conjecture implies finiteness of real structures. Okay? Yeah, but the proof is more or less in our paper already. So okay, let me give you a sketch of proof of theorem 2 for automorphism, let's say. Okay, so well, yeah, you look at the automorphism of X acting on the narrow series space. Okay. First thing to realize is that the kernel is finite. The kernel is very easy to analyze. Kernel is finite because what is a kernel? Kernel is an automorphism that preserves all the line bundles. So in particular, you can say it preserves some ample line bundle. Therefore, it's a polarized automorphism group. So it's an algebraic group, but it's discrete because there is no tangent vector. So it's a discrete compact group that is finite. Okay. So we are reduced to show that H1 of gamma without star is finite. Okay. We just want to show this is finite. Of course, we have also to bound. Yeah, I should use G to show that for any finite group G, we want to show this is finite. Anyway. Okay, I should say we have to show that. So I'm sorry. We have to show the same thing. Show the same for automorphism star, which is the image of rho. Okay, we are going to show there are only finitely many finite subgroups up to conjugation on this image. Okay, let's pick. So let's pick a subgroup then. H subgroup, finite subgroup. Okay. Let's show that up to conjugation, I can put it into some fixed finite set. Okay. Let me pick a fundamental domain. Let me call it sigma. So you can take a point, alpha, let's say inside the ample cone. Also the narrow series. Okay, you can take an ample divisor. Let me consider it as a point in the cone. Then one can assume that alpha is fixed by H. Okay? Because H is just a finite group, you just do average. I mean, not average, but you can take the sum of all the actions on alpha and take the sum. Sorry?
I cannot read. It's the ample cone.
Ample cone of X intersect with, I'm taking ample divisor on X. It's a narrow series of X. Because ample cone is like a real thing. I don't want to take, yeah. So take an ample divisor and average it, you get a fixed ample divisor. Okay? So yes, so alpha is fixed by any element of H. But by the Morrison-Kawamata-Kuhn conjecture, proved by American-Verbitsky, there exists a group element such that G X or alpha is inside this fundamental domain. Let me call it beta. Okay? But the beta has the property that beta is fixed not by H, but by a conjugate of H. Which conjugate is that? G H, G inverse. Okay? This is the point that is fixed by this conjugate. But this is in the fundamental domain. So if it's inside, really in the interior of the fundamental domain, then there is no such automorphism. Yeah? But unfortunately, this beta could lie on the boundary of this sigma. But again, by some generalized version of the Siegel property, I learned this, I didn't find any work of Siegel here, I can find, but I learned this property, precise statement in a paper of Lu Yangha. So I want to put Lu Yangha here. He called it Siegel property. Then it implies that G inverse is inside some finite set. It's like G, why not? G inside. Such that some face. So this is the unique face. Pi is the unique face of sigma whose interior contains beta, such that pi sigma ample cone is non-empty. Okay. So obviously, by this argument, this set is inside this set, but this set is finite. Siegel property says that this set is finite. So this subgroup, after conjugation, this subgroup is inside a finite set. So there are only finitely many choices. So H is finite. Up to conjugation, there are only finitely many choices for such kind of H. Okay. Now let me finish by giving you some remarks.
I'm confused because up to conjugation is contained in a fixed finite set.
Yes.
So
yes.
This proves that the conjugacy classes of finite groups are a finite set. Not
Yes.
that the subgroups are a finite set.
Yes. On conjugation. Up to conjugation. Yes. Yes. Of course, yes. Here is also modular conjugation, by definition of H1. Then, okay, where am I? Yes, some final remarks. So I announced the same result for birational. So for birational automorphism of X, one uses Markman's theorem. Markman's so-called movable cone conjecture, movable. I mean, conjectural theorem, he proved it, okay? So similar, well, it's not a conjecture of Morrison-Kawamata, but it says that for hyper-Kähler manifolds, if you look at the movable divisors, they form a cone. Movable means that the base locus is of codimension at least 2, okay? They form a cone. Then the birational automorphism group naturally acts on this movable cone. And the theorem of Markman says that it has a finite rational polyhedral fundamental domain. Then just run the same argument. You get that the birational automorphism group has only many finite subgroups up to conjugation. And similarly for the finite presented in this. Okay? And another remark is that Takamatsu very recently this year showed that for any finite extension of field finite extension of fields of characteristic 0 Then the twists, they are finite. So the twist k prime k of x, so yeah, and any x hyper-Kähler defined over k. So for characteristic 0 field, hyper-Kähler over that field is just a smooth projective variety over k such that the complexification is a hyper-Kähler in that sense. And the twist is, the forms. It's called k forms of k over bar. So it's like y, a variety over k such that y over k bar is isomorphic to x k bar as k prime varieties. This is finite. Over k isomorphism is finite. Okay? So there is no story of complex field or real free fields. It's just any finite extension of fields. And his proof, unfortunately, one cannot use the k automorphism or dianalytic automorphism group. So he has to use some other tricks to like bound a polarization and use the finiteness variation models. But again, ingredients is again Morrison-Kawamata-Kohn conjecture. He has to use it twice. Okay. But in the end, it might has nothing to do with real geometry. I'm sorry for wasting your time. Thank you.